Today we will start a new topic, which is the topic of eigenvalues and eigenvectors. For this we need first a definition. When we talk about eigenvalues and eigenvectors, we talk about linear maps, and thus we can talk about matrices. So we assume a square matrix A first. Then we have the eigenvalue lambda and the eigenvector mu of the matrix A to the eigenvalue lambda if the matrix A times the eigenvector is the same as the vector multiplied with the eigenvalue, which is a number. So this here actually holds true for any or for each linear map that preserves dimensions. That's why we have a square matrix A. If we see the vector mu, the eigenvector, as a vector, really, then of course applying the matrix operation does not change the direction of the vector. It only changes its size or its orientation. It may become longer, or it may become shorter, or it may turn around into the negative, but the direction of the vector does not change. We will see that, of course, a vector space does not have to have these classical spatial vectors that we think of, but it can also be functions. And if we talk about functions, then this operation does not change the vector, the function. A linear operation that doesn't change the function up to a factor. So, why is this important? Where do we need eigenvalues and eigenvectors? For one, for linear differential equation systems of first order. This is actually the same as linear differential equations of higher order. You will notice that many of the terms that we will come to are already or have already been used in the theory of solving linear differential equations of second and higher order. You may remember that the differential operator is a linear operator. Creating the derivative of a function is a linear map. So you can say that on the left-hand side of our equations later we will have the differential, and on the right-hand side the matrix. And this will then lead, of course, not to vectors as eigenvectors, but to functions as eigenvectors, the so-called eigenfunctions. Another part where eigenvalues and eigenvectors become important, and again the eigenfunctions, is the whole theory of the Fourier analysis. When you look at the eigenfunctions in the Fourier analysis, you may have heard already the term of the eigenfrequency. The eigenfrequency is just the imaginary part in an eigenvalue. If you have a complex eigenvalue for a function, we will see this later, this can then be seen as the eigenfrequency. And the basis vectors that we look at when we look at the Fourier analysis are oscillating functions with these frequencies. Another very important point is rotations. If you have a rotary matrix and you multiply it with another rotary matrix and you multiply it with another rotary matrix, which means you are doing 3 rotations one after the other, you get one single rotary matrix. you of course have no idea what this single rotation now is in angle and in rotation axis. To find out this rotation axis and the rotation angle, we need to find out the eigenvector and the eigenvalue of this rotary matrix in the end. Why that? Well, if I have a rotation axis, then there's only one vector that does not change when I rotate around it. Any vector that I rotate around it will change unless it is exactly the rotation axis. So I am looking for, when looking at rotations, I'm looking for the one eigenvector with a resulting eigenvalue of 1. One last point. Is the question whether you can transform your matrix into a diagonal matrix, whether you can diagonalize the matrix. This is always possible if your n times n matrix has n different eigenvalues. Sometimes it's even possible if not all eigenvalues are different but some are the same, but this will be beyond the scope of our lecture. With the diagonal form and the transformation of matrices, which will be a whole own topic, we are looking actually at what is a good basis to express our matrix. The benefits of finding this good basis will be discussed later.